Hi guys, I'm Prof Joe. I'm a professor for automation and measurement technology at the University of Applied Sciences in the very south of Bavaria in Kempten, which is in Germany obviously. This is part of my lecture on measurement technology, which indeed is AI accompanied, so you have some link to a large language model below there which gives you all the content and learns all the stuff together with you, though that I am just giving you some core aspects, some basic explanations and some further knowledge around that stuff. Okay, this is chapter 6 about measuring resistances, part 2, now dealing with circuit bridges or measuring bridges. What does that mean? I will just write down a measuring bridge to start with. The idea is very simple, which is we don't use two resistances or one resistance and a whole lot of current or voltmeters, but we use 4 resistances and are only interested in the voltage within that bridge. There are some numbering of the resistances, which is R1, R2, R3 and R4. And talking about a measuring bridge, most of the time that resistance R2 is the one which is not known, which we are looking for. So the other 3 resistances, most of the time, are known resistances. We can assume to have a certain value. In this form, it is also called the Wheatstone measuring bridge. The thing Wheatstone did was he was thinking about how to measure resistances, and he hadn't anything like a modern multimeter which provides you with a absolute correct usable value of your voltage. What he could do was he could measure voltages somehow. At least he could see if there's a voltage or there's no voltage quite well. So the only way he could think about resistances was to compare resistances to each other. And that's the idea behind that. Measuring that voltage and looking when that voltage is 0 provides you with an idea of how big that resistance, that unknown resistance is. Let's write down some equations for that. The most important one, it's easy derivable. Just ask the large language model to get hold of an derivation of that equation, but it's an equation one can know, one should know, because it's quite often used out there still. So it's nothing more than the voltage we are applying to that bridge times R2 times R3 minus R1 times R4 divided by R1 plus R2 times R3 plus R4. Okay, that tells us a few little things. Thinking about that bridge as Wheatstone did, we are interested in the fact that our differential voltage over here is 0. And that means we get a balance condition, which is Rx equals R2 equals R1 times R4 over R3. Which can be easily derived by setting that denominator equal to 0. That balancing equation is great because using the resistances R1, R3 and R4 we can get somehow a value for our search resistance R2. But at the same time one thinks, okay, nice, but unusable. Thinking about that in standards of today, that looks quite unusable because we have to vary R4, R3 and R1 so long until our voltage drops to 0 and we can calculate R2. So we have to search for that balancing equation varying other resistances. That was something Wheatstone could do quite easily, or which was the only thing Wheatstone could do actually, because he could change those resistances. He could just calculate somehow a ratio between the different resistances. Nowadays, that's not enough for us. Especially we don't want to search for a balancing equation or balancing condition. We just want to measure a voltage and very rapidly get to know a value which equals our unknown resistance over here. For that reason, and that's quite obviously, we are using that measured differential voltage to calculate resistance for R2. Meaning, looking at a contemporary example, that would mean we would choose all other resistances the same and only search for our unknown resistance Rx, and that would give us a differential voltage which can be derived by only putting in those values into that equation over here, which is U0 over 2 times Rx minus R over Rx plus R, and that indeed can be solved for Rx, which then is Rx equals R times U0 plus 2UD over U0 minus 2UD. And that's something we can use nowadays. We just measure that voltage UD over here and we get that unknown resistance Rx over here. Now another question arises. Okay, you're right. We can now somehow measure that resistance by measuring that voltage. But again, compared to measuring a resistance using a reference resistance, as I explained in part 1 of this chapter, why the heck should we use 4 resistances and not only 2? Why are we using 4 of them? The reason for that lies in the behavior of all of those resistances altogether. Because we have the possibility to put in several resistances. Having a certain behavior, we are able sometimes, or by just choosing it the right way, to, for example, compensate for temperature variations in those resistances. Meaning compensating for changes in the resistance we are not interested in. Just to give you a short example of that, we'll keep our bridge over here. Imagine we are placing some resistances in that bridge. I will just write down some equations for them. So imagine we have a resistance which is able to measure the gas concentration, which reacts to gas concentration. So for example, R2 is some base resistance, R0, plus a variation in the resistance triggered by the gas concentration. That's awesome, because now we can measure gas concentrations using resistances. I will talk a little bit more about those things in part 3 of this chapter. But let's assume, as every resistance changes due to the temperature, also this resistance may change due to the temperature. So we also may have a variation due to the temperature over here. And now that's something we don't want to see. The thing we want to see is the variation due to the gas, but we don't want to see the variation due to the temperature. And now let's be smart and just place for our resistance R1 another gas sensor which we do not supply with gas, meaning we simply isolate it. So we don't have that change due to the gas concentration, but still we have the change due to the temperature, isolating the very same sensor from the gas around it. Now the other resistances may be quite simple and equal to the base resistance. And now Let's put that into the equation we already know, which is R2, R3 minus R1, R4 over R1 plus R2 times R3 plus R4. Let's look at that. Just putting in those values results in R0 plus delta Rg plus delta Rt times R3 is R0 minus, and now we have R1 times R4, and that is R0 plus delta Rt times R0, and now in the denominator we get something like, just summing it already up, 2R0 plus 2 delta Rt plus delta Rg times, and now R3 plus R4 is 2R0, so just write it down. So now we see we can just cross those R0 out, and we can look at the denominator and look at the things which will remain. We see R0 minus R0 vanishes from the denominator. We see delta Rt minus delta Rt vanishes. What stays in the denominator is only delta Rg. Just let's write down that once more. We get a delta Rg over, and now let's sum up that whole stuff. 2 times 2R0 plus 2 delta Rt plus delta Rg times U0 for sure. And now that is interesting. Why is that interesting? Because we see the dominating part of our equation over here is our delta Rg. It's small, it's near to zero. It's a small variation in the resistance, but it's in the denominator. So that's the dominant part of our whole equation. Now in the denominator we see there's R0, and now let's assume some values. For example, let's assume we have R0 having 100 ohms, and now let's assume our changes are around 1 ohm. That's a realistic assumption, holding for example for a whole lot of temperature sensors and also for a whole lot of other sensors. Anyways, now we divide by 2 times 100, 200 ohms, plus 2 ohm plus 1 ohm, making the difference of not caring about those, the difference of dividing by 200 or dividing by 203. Obviously, that's nearly the same, meaning that dependencies on the variations due to the temperature and due to the gas concentration in the denominator are not dominating. They are nearly irrelevant, meaning we can do a very good approximation by just leaving them away. Again, leaving those away is the difference of dividing by 203 or dividing by 200, just for our example. Meaning, we get a very good approximation which only has the change due to the gas concentration divided by some base resistance R0. That is awesome. Why is that awesome? Because, yeah, you're right. There are PC systems out there which are able to compensate or to calculate variations due to the temperature and so on and so on. But they have to have all the data, all the environmental influences to get that all right. And that's very complicated. Although it's possible, maybe. People don't do it because we have that easy possibility to get rid of, for example, that temperature dependencies, those temperature influences, by using 2 times the sensor, by doubling the sensors. And that can be done in any which way, crossing out only the thing we are looking for. Meaning, when you are looking for not a gas concentration, but for example for the resistance changing due to the magnetic field. We always can just surround one sensor by some metal, hindering the magnetic field to touch it, and by that remove it one time in the nominator, and by that getting the nominator to be dominant in that change we want to know about. All other changes due to the temperature and, for example, due to the gas will just cross each other out in the nominator. And that's very usable, and that's very practical, just to measure exactly that change in the resistance we want to know about. Okay, there are many ways you can place your resistances over here, your changes. You can have 4 sensors in there, all having different variations, and so on and so on. All of those combinations have names like quarter bridge, half bridge, or full bridge, or whatsoever, but that's not important to know about all of those specific facts. The important thing is to know about that formula and know how to use those resistances to only get the variation in your nominator you want to know about, and to have all the other variations to cross out each other. And that's, to be honest, not very complicated to think about that equation, especially only for the thinking for the nominator, thinking about the nominator at all. Having said so, that is part 2, talking about measurement bridges, about circuit bridges. This type of bridge, measuring our differential voltage UD, sometimes is also called deflection bridge, because we are measuring a deflection in the voltage UD. But altogether, it's the same concept overall, which allows us to compensate for environmental effects. And that's the very important fact. We need to know why those bridges are still used. If you like that stuff, feel free to subscribe. And in the last part of this chapter, I will talk about some physical quantities we can measure using resistances. And till then, have fun.